yeah, mild singularities would be nice, but well. Okay, so this is a joint work with Joseph Palmer. And technically, how should I put it? I mean, this is a somewhat longer going program. And I think the idea of everything started about 10 years ago. And concerning the height or concerning the handwriting? I mean, right now I'm not writing at all. So, okay, good. I'll try my best. Good. Let's maybe just write down the setting and then I try to explain a little bit what's going on. Okay. During the whole talk, we are in dimension 4 on a 4-dimensional symplectic manifold. This manifold should be connected and compact without boundary. So let's write this down. M omega connected symplectic slower. When it's incursive, it's a little bit more. Okay. Well, then compact, better, without boundary, and 4-dimensional. And I'm working here with completely integrable systems in the sense of Liouville. So I have 2 integrals on this manifold. So let's say M omega and F is given here by J and H. And here I say this is a completely integrable system. Good, good. And what I want to have here for, of course, is that, I mean, the Hamiltonian vector fields, xj and xh are almost everywhere linear independent. And of course, I mean, here they should Poisson commute the functions. So I want that the Poisson bracket of J and H, which is here given by the standard symplectic form of the Hamiltonian vector fields, vanishes. So I mean, classical Liouville setting. Okay, and if I have this here, certainly I also have a group action. So how should I put it? Let's maybe put it here. In particular, I get that if I consider the flows, phi j and phi h, then we get an action of R2 on M via, we're just, well, let's start here maybe, R2 times M to M, and we're sending S and T applied to a point X is just phi S J of phi HT of X. So we're just flowing manifold. So I mean, taking point X, first we're flowing here with H, and then we're flowing here with J to wherever we want to get. Okay, and I mean, one can see already here, and I mean, if one compares it to the various approaches in the previous talks, that you can consider these things from various angles. I mean, you can say, well, I look at vector fields, You can say I'm looking at flows, I'm looking at actions, I can look at vibrations, and so on, and so on, and so on. And more or less each and everything at some point shows up when one's really looking at the details now of our paper. I mean, we updated it about, I think, 1 or 2 weeks ago on the internet. Now it's from the 50 pages last year up to 60 pages, but also improved with a couple of nice pictures. And what one actually, or the idea what we want to do, or did more precisely, is the following. So if you here just have a look at a classical definition by Dyson, this was, I think, in 88. Of toric systems. So, I mean, with toric, I mean that those two integrals here actually induce us here in periodic flows. Technically, I have here an action instead of R2 of 2 on M. And so let's say here we have some M omega JH, and the action we get is here in S1 times here in S1. And I mean, in this classification, always is assumed that everything is effective. So let's maybe put this here too. Only the identity acts trivially. So you don't want to have that something is double covering, technically. Yep, Pesor, yep, precisely. Okay. And here we have this situation. And I mean, the classification is actually very nice, because when you look at what is actually classifying this thing here, it's just the image of the momentum map. So in this situation, it's classified by f of m, the zone polytope. And f is here just, I mean, both together. Good. And on the other hand, in classification, that is not as old as that one, but still already a couple of years old. Let's maybe try to put it here. This is Yarka-Schon's classification of Hamiltonian S1 spaces. So let's put this here, maybe. I think it was 99 when this was done. And Hamiltonian S1 spaces sounds somewhat, how to say, fancy, but technically what it means is you have in the setting here m omega and just one integral. And that thing here should generate an S1 action effective. Okay, so, and the question is a little bit, of course, then here, how, which means was, or in which terms was the classification? Here it's just the image of the momentum map. And here it's done by means of some I'm in dimension 4 always. Okay. Okay, and this, so here the classification is, or the invariant is a graph And this graph consists of just fat vertices, some edges. And we will later what like and how it affects actually what you want to do. Okay, I mean, what 1999 was when you have here these toric systems. I mean, if you just forget here the age, you end up with an S1 action, right? And so technically you could ask yourself, if you can go down to this classification, and if you can go up, so extend, meaning finding age. Such that the whole thing is toric. And yeah, gave here precise conditions when this is possible, so sufficient and necessary. Namely, let's say, put here, let's put here Hamiltonian S1 spaces. M omega J with, and on the one hand, I mean, I told you there are two types of vertices in this graph, and the fat one, they stand for fixed surfaces. And here, if you want to be able to lift, these fixed surfaces may only have genus equal to 0. And on the other hand, the action can also not be have too much action, in the sense that whatever kind of non-free orbits or things you have, it cannot be too wild. So let me just write it down here. You may have at most 2 orbits per level set, or let's say per interior level set of J. Trouble is that I don't have enough space here in order to make a reasonable picture. This means a little bit, it's not totally schematic, not really drawing here something where I really have an action immediately that I could write down. But this kind of setting here would allow that you could have edges here, so something like this. If your coordinate system, here would the H go up, and here goes the J. You have something like that, or you could have 2 of these points on top of each other, or you could have an edge, I think, and somewhere a point underneath. So, but technically, whenever you cut here through the graph, you do not want to have more than 2 hits. This is a little bit the condition that you can lift, and also when you actually push down, you don't get anything else. Okay. And then, of course, comes the question, what may be sitting between? And in particular, if one has here the full thing, to what this may lift. And here, actually, how should I put? Let's start with something that relates to about 9 or 10 years ago. In, I think the papers are from 2009 and 2011. So this is the classification by Pillai and Van Gogh. Let's say just take the average 2010. Classification of so-called symmetric systems. And now that we actually have all these definitions, let's maybe just write down what this is. So symmetric means well, in a non-compact situation, you would need one of the things to be proper. It would be an integrable system. Also, next, semi-toric means that there needs to be something which is somewhat toric. So they said, well, okay, let's ask that the J induces an S1 action, which should be effective. Moreover, if you want to classify, you don't want to have two nasty singularities. They said all singularities of F given by J and H should be non-degenerate. And now comes something which is somewhat really annoying and really just artificially imposed. They don't want to have any kind of hyperbolic components in the sense of this classification by the local normal form. And this technically means then that when you take these things together as rank 0 singularities, you have elliptic and focus, and rank 1, you have elliptic regular. So it's more than toric, where you only have elliptic, and elliptic regular, since you have focus, but it's also not such a big jump. But in terms of classification, let's maybe put this here. So we have here then M omega JH, and the action is S1 times R. The R, since, I mean, here on the focus fiber, I mean, you have something that goes completely around and therefore is not periodic. And the classification depends always a little bit how you write it down, but usually the easiest way to explain things is that one says this in terms of 5 invariants. And one of these things is a generalized polygon. Okay. Classification of symmetric systems, and this is in terms of variance. They defined some but the idea. And so technically what their way of defining their isomorphism class means that the J, or this S1 action that is left here, is some skeleton. And this is also somehow the idea which we then took on the way to get here and to lift them. So one really can think of the J here as some how should I say, the whole thing. Okay, so then we come here. Certainly you can forget H. And you can, let's put here also maybe a big K for Cachon, that was. And here, same thing, you would like to forget the H, and you would like to be able to lift. So comes the question, what is what? The way down, this I did together with Silvia Sabatini and Daniele Sepe in, I think, 2015. Or more precisely, the preprint was certainly 1 or 2 years younger, but published, I think, 2015. And I mean, the going up here is together with Sylvia and Daniele and Margaret Symington. And this is, well, the math was theoretically done, but it's not yet written up because we wrote this thing down. Let's maybe here. Okay, I first write it down, then I explain what happened. So we have here, then Hamiltonian S1 spaces. M omega J with With the genus, it's the same thing. Also, all possible fixed surfaces can only have genus 0. But here we can have a little bit more fun or adventure. So we can have at most 2 non-free orbits, but technically non-free, non-fixed. Per, let's say, internal J level. Let's maybe here again just make a drawing what I mean. Again, if you're here looking at it in the coordinates H and J, I mean here, when we're coming down, worst case, here we can hit more things as long as we do not hit more than 2 of these edges. So you can have here a couple of points over each other, or you could have here something, as long as we don't have 3 lines above each other. But I mean, these things certainly could happen here. So the question comes how to get there. And now let's maybe explain what's happening going on here. So once we did this, I mean, Silvia and myself were still in Lausanne as postdocs, applying for positions. Daniela, I think, was still in Lisbon, also applying for positions. And then, more or less at the same time, everybody got tenure track or permanent positions. And then, I mean, how should I say, real life hits you. And from being a nice engine post, 20% of research, you go to somebody who has to struggle with administration, teaching, and whatever else, and epsilon time for research. And if you at the same time have to coordinate 4 people spread over 3 continents, it gets difficult. So I mean, technically, we gave a couple of talks about this, but someone never really wrote it down. And now the trouble was then when via some totally different ideas, I ended up doing this here together with Joey. There were several things to keep in mind. On the one hand, since there was already something going on and we didn't want to encroach on the mass here, but it was not yet published, so we had to somehow circle around, which was possible. So this paper is hopefully at some point this summer finished. And what we did here is sound and safe, although the thing is not yet finished. It's checking out how to do it, but it worked out. And here I don't only make a dot because what I'm actually put here is not yet classified. So I mean, here this arrow down with forgetting H always meant at the same time I can somehow match the classifications. So I can find what I forget back in the lower classification. But let me write down what we have here. Here we have so-called, so this is whatever, 21. Definition of so-called hypersymmetric systems. And I mean, we've been beaten up quite a lot for the name for various reasons. Let me maybe just define what systems are. So this is hypersymmetric. Well, I mean, of course, if it's integrable, we want to have that J induces an S1 action. And now the only thing we want to say here is that how to formulate this actually, in order to keep it short. Okay, let's put it like that. All singular points non-degenerate. Except maybe finitely many degenerate ones of parabolic type. Okay, so let's see what this means. First of all, here the no hyperbolic whatever drops. Technically, you admit everything concerning singularities that is non-degenerate, but the trouble is that in particular the hyperbolic regular things, they may come in, let's say, a family, or when you draw it in the image momentum map as a line, and the thing may end with degenerate points. And I mean, here, these parabolic points show up, and these are, let's say, the nicest possible degenerate things you can have from our perspective. Or orbits. And it's a little bit like, how should I say, regular points is your full rank of the differential. Singular is the differential phase, but you have conditions then, or nice condition on the second derivative. And here, I mean, somehow the second vanishes, but you have condition on the third one. So a little bit that's the idea. So they are the nicest ones and quite natural and so on. And now comes another feature a little bit. If you have this here, this actually implies that although you admit here a priori everything concerning non-degenerate singularities, having an underlying S1 action excludes hyperbolic. I mean, you just can't have that. So, or let's hyperbolic does not appear. Voila. But apart from that, I mean, you can have a priori everything. And so, I mean, technically, this is, I think, a quite natural class of systems. And one can find examples where one sees clearly that you need to admit something degenerate, and parabolic points are, as I said, quite nice ones. I should maybe add here something else. Let's see. Should I add here something? Not yet classified. And with classified, I mean in a symplectic sense, not topological or something like that, like it's also there. And I have here as action. This I also should say. Action is still S1 times R. And here, I mean, M omega J and H. Okay, so. Under the point of view of classification, admitting hyperbolic stuff, if you want to do something concerning combinatorics, like here with the polygons and so on, is a little bit annoying because the image of the momentum map, I mean, is not just a flat, nice polygon. It may have, I mean, there may be branching offs. So from that point of view, it's not so nice as, let's say, the polygon here, which is a nice polygon, which is a little bit wiggled. As far as I know, I mean, I think Sue Tolman at some point gave a talk during the last months or weeks that she's together with Daniele Sepe busy to try to come up here with some other way of lifting, namely by not admitting hyperbolic stuff, if I understood it correctly, but by allowing much, much more degeneracy. So, I mean, the advantage they then have is, or what they aim for, as far as I know, no preprint has so far appeared, is they get something like a polygon because they stuff all the other things they somehow need to stuff somewhere into the degeneracy. But on the other hand, I mean, when one comes from dynamical systems and you come along and you say, well, okay, we're looking at a class of systems where we do not admit hyperbolic, it feels somewhat weird. So it's a little bit of balance. And I mean, I think what may be more handy or not, one may see the very moment one tries, let's say, to classify something here. Then I guess one sees what makes more sense, or which is in which situation may be more natural. Okay. And yeah, I think here one can actually see already quite nicely what the trouble is with having more than two of these edges. Because when you lift, the edges go to the upper or the lower boundary of your polygon. And if you have here a nice proper decent polygon in the sense of something convex with overlapping and no branching, you can only have two, no space for more. So anything which would show up here, when you have here a graph with a couple of these things above each other, here it's not edges with an example. What's happening here is, but so let's say this one here goes to that one here, let's say, goes to that. And the one in the middle, you still can have some kind of a branching point where another leaf of the image comes off. So it's a little bit like, imagine here, the table is the polygon. And then I would have here, I mean, so here, this is one of the edges. Here's the other edge. And I need the third one. In a normal polygon, I can't have that. But by using of hyperbolic regular points that appear in the middle, you can just glue another leaf to it, and then you get some kind of branching. And then that way you can get another edge in the middle of a polygon that is still quite natural. So this is a little bit the idea. Yeah. Let me maybe make a drawing, then we see what's happening. I think I have 10 minutes, so let's try to do some example, and then one maybe sees what's going on. Okay, this is not. Okay, now let's try to get an idea how the whole thing is actually done. So proof by example. Okay, let's maybe start out with some whatever kind of Hamiltonian S1 action. And that thing, this is Yael's classification, that thing has this graph. Now I'm writing just down the graph. And let's take, for example, something that has here a fat edge. Then here, let's say, something which is labeled 2 for the isotropic group. With a 3. Middle, a non-fat point. Let's have here, let's say, another edge. There, what? Something like that here. 3, 2. Good. So I mean, technically, as you can see, these graphs, they can have fat points, thin points, and a bunch of edges that can be connected at some of the non-fat points. Now, we would like to have here a Hamiltonian system that has this one here as underlying S1 thing. Okay, how do we do this? Now, remember, Yael showed that not just a classification, but she also showed that each of these Hamiltonian S1 spaces actually comes from one of three basic Hamiltonian S1 spaces via blowups. So from here, we can go backwards to the minimal model underlying that one. And if we didn't mess it up, for example, for us worked nicely having a fat edge here and having just one edge here. If you draw here for the corresponding Desson polygon, then you also see what's going on. I try to draw it a little bit correctly above. Look. Okay. Voila, here. When you look at under the point of view of toric systems, vertical polygon in the S1 action, if I go here, J, and up here with the H, so I get here a fat vertex. It gives me that one here. That one gives me that one here. And here I can check what kind of stabilizer it has. And it's stabilized by so-called set-modulo 3 set in the situation, or a set K-sphere. Okay, so this is the corresponding thing. Oh, one way or the other, we want to have all these kind of things here. Okay, first, let's do something easy. Let's try to get here another edge. So next one, there's a so-called operation of blow-ups. Here it's a toric system, so we do a toric blow-up or blow-down. And the idea is we just chop off here the nose. So what we do is, in our paper, we have it nicely with the correct, where is it? With the correct, I mean, when you this stuff, you just need the proper relations of the edge, what kind of slope they have, and so on. And we have worked exactly that example here out. I just don't find the page. And there, I mean, you can check what kind of points there are actually. Okay. Good. So we have this one here. We get here again the fat one here coming from the vertical thing. We get here that thing here still labeled with 3 from the slope, and here something labeled with 2 coming from the slope. And that thing is still Desson. Now we have here some stuff. Well, I didn't draw it perfectly in line, but we have here some stuff, 3 things above each other and of different types. So let's see how we can get that. What one now wants to do is, well, we need here something, more points and more whatever. What one can do certainly is, if we're just chopping off here something, we get here something elliptic, and we could try to do a nodal trade and get the elliptic inside as a focus. This idea somehow you can generalize, and you call it an asymmetric blow-up, and then that thing actually gives you something like, I think here again, you can perfectly compute the slopes and so on by the monodromy that needs to show up. So you get something like, I think here like this, then something like this. Then again, it comes down here. And again, you have this kind of foot here. And I did some, no, this is correct. Something like this. And here on this vertical line here, we have So this is a symmetric polygon. And this here is then symmetric blow up. This just here's just a blow up. Toric. And here was symmetric blow up. Good. And if you now look here, what's happening? We still have some kind of fat, whatever here. But we also get from there, I mean, that thing here is now just fake. This doesn't exist anymore. 3 points. We still have here that thing coming from there, plus that thing here. Next one in. Yep. I need one picture and a polygon. Okay, now we want to get these things here. But what we're doing now is only happening upstairs. It's not yet happening downstairs. So here, concerning the S1, but I mean, this toric blow up is known since quite a while. I mean, also the underlying symmetric blow, underlying symplectic cutting, gluing, and so on is quite known technique. The symmetric blow up, I mean, we had to do it a little bit differently than it was here devised. So, but I mean, this is also around since a couple of. But this here, technically, the idea as such, I think, in dynamical system is also around quite a little bit longer. So what we're doing here is we're gluing in a flap or stuffing in a flap. So what's happening is and I do here a better picture. Okay, I think this is it. Good. What happened here was we replaced, let's call this focus blow up. And what's happening here is this is Durlin. What you can do is, if you have somewhere a focus, you can replace it by something that looks locally like this here. And I mean, let's say here's a background. Here we have the polygon back. So I mean, here we have just something nice, one sheet. And here, I mean, this is the background, but that thing here is like if I would take here my piece of paper, glue it on the wall. So it's actually here a double cover, except that it's glued here. So it's have a branching along this side here. And these things here, they are hyperbolic regular. Here you have a parabolic point, here parabolic, and here is elliptic. Okay, so this is what these things stand for. So far, I mean, this doesn't change anything down here because instead of mounting a focus, I'm now just having here an elliptic, but down here, well, the thing is fixed point for this one action, who cares? In order to get these kind of things, we are now having to do here blow-ups on this flap. So what's happening here is and I mean, now when you do these kind of things, also that thing I mean, actually, this here already got somewhat wiggly. So if here somewhat wiggly polygon. And here, let's see, I think in my convention, I have here this flap. I originally had here this one point, and I'm doing two chop-offs. So technically, I get here something which looks like pretty much eaten by a mouse. And I mean, here we still have it glued. So here is hyperbolic regular, but here we have two elliptic points. And these things here on this polygon, they give us here the two edges in the Cauchy graph. And I mean, that one stayed as it was. And up here, we did the same thing. So we cut off here the elliptic thing. And then look, that thing here. Actually, I forgot to cut off here one. There we need another one. We need it to be like this. Yep, I think. No, another one. Like this, I think. And that way we should, if I'm not wrong, get this one from that side here and that one here from there and there. And I mean, next point is you need to check that whatever you do down here actually doesn't mess up being hyper symmetric up here, but one can check that, and this actually does what one wants it to do. The underlying technique was, in order to construct all these things, that at some point we passed to the, or we looked at the reduced space, and then tried to consider the H here on the reduced space. I mean, where we always had to construct here things as some kind of Morse function on this two-dimensional reduced space. And then you have a bunch of more flexibility or more possibility just to draw what you want to do. And then it's, at least, I mean, geometrically, it makes sense what we're doing. And I sincerely hope that we don't have any kind of problems with the epsilon and delta and stuff like that. And with that, I thank you for your attention. Ugh.
So in your construction, hyperbolic elliptic doesn't have to.
We don't need it.
Yeah,
I mean, so far we can do without it, but I mean, as useful class, this makes sense, I would say. I mean, I guess if you do other constructions, you may get it also that way, but I mean, we were happy that Holger and Alvaro already provided something that worked out, and then we used it. And yeah, I think Hamiltonian Hopf bifurcation. I mean, that one here, I think this is what. I mean, here we're just chopping off. I mean, this is again, this is your blow up. I mean, this is, how should I put it? I mean, if you chop off such a nice toric edge, or if you chop off something which you first want to straighten out, doesn't matter. So I mean, technically, this eating up stuff here is toric blow up or blow down. And let me just try to find here somewhere here. Okay, this is page 42 of our paper. Here you find it properly done and not so squiggly, and with the right ratios. So I mean, there you can check if this actually comes out or not. And we try to, I mean, in the paper, we try to give a decent introduction about, and then we also have a quite long chapter 2 where we try to summarize all these various things that show up, such that the paper is pretty much self-contained. So you don't have to read the whole literature or dig up what's happened in the last 10, 20, 30 years. So it's pretty self-contained. And with lots of pictures, I hope. I mean, let's put it that I have not yet seen what Sue Tolman and Daniele really did. I saw once a talk about what they were thinking to do, but I mean, when you squeeze something think in 40 minutes or 30 minutes or whatever it was, that Sue tried to explain what she was doing. I mean, I don't really remember the total details. The main difference, I think, why they are doing what they are doing is when I now really draw the kinds of things that show up in our situation. I mean, you have here some kind, how should I say, you have here the underlying polygon, and then you have here the flap coming up, let's say. And so when you look now at the, well, bad picture. Let's just draw it like classically like this. And if you now look at the fibers, I mean, here over the hyperbolic regular stuff, let's say you have these two toric glued on top of each other. And I mean, here over the parabolic stuff, let's say the upper torus here degenerates. So you get some kind of torus that is created from a teardrop, something like that in the inside. And I mean, here, when you look now at this point here and you look at the fiber, well, I mean, you have an elliptic point up here coming from there, but here underneath, I mean, from the thing on which it is lying, you also still have an torus flying around. And here in the middle, I mean, when you look at the fibers here, it's disconnected too. So, I mean, you have two tori above each other. And so, I mean, you want to classify, and usually when you do these polygons, you really want to have connected fibers, blah, blah, blah. And I mean, this you certainly don't have here. And mm-hmm. 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 Yep. Yep. I mean, let's put it like that. We also didn't have really looked at it, but I think here this class of systems here with the parabolic stuff is pretty much generic / natural. So yeah, precisely. Hyperbolic can't happen due to the S1 act. Everything else, everything non-degenerate, which can happen, may happen, plus maybe parabolic. So I think it's pretty natural / generic. And so for that kind of reason, I think that our approach is at least more natural for people from dynamical systems. But of course, if you want to have a nice, decent polygon with connected fibers, I mean, sorry, this. Yeah, and I mean, how should I put it? I mean, when Oro and Sun were busy here with their semi-toric classification, polygon. This was the main reason. I mean, they wanted to preserve as much as they could from the toric world. And well, I mean, there you still can do it. I mean, you can straighten the stuff out such that it is toric modulo having some choices. But here, I mean, well, I'm not really sure how one could maybe reason here, but we have not yet tried actually. And I mean, we're also not that fixed on this having just one layer polygon. And I mean, this also the name here. I mean, when we came from, oh yeah, toric, semi-toric, something with hyperbolic and semi-toric, hypersemi-toric. But on the other hand, I mean, technically what we're having here is we're having an integrable system with an underlying S1 action plus naturally appearing nice degeneracies. And so technically, I mean, if we could have already proven that this thing is generic, we just would have probably called them generic S1 systems or something like that. But we didn't want to give it a name because in case one can prove that the thing is generic and we give it a stupid other name, then you have again conflicting notations. And for that, we decided to stick to the name here. This, there's a really silly reason, namely here their classification is in dimension, this classification is in dimension 4, and so we first had to go at that. concerning high dimensions here with the symmetric stuff, there are a bunch of works by various, I think, PhD students or postdocs who tried one thing or the other, and then comes also X1, whatever I think Yael and Sutorman are working on. So it's a bit so philosophical what you want to do actually.